Okay, for Newton's third law 1.1, topic identified. Newton's third law states that every action has an opposite and equal reaction. With that being said, it means that the action and reaction forces always will occur in pairs. They'll never be just on their own. He also wanted to point out that the two forces act on different objects at the same time. So yes, they're still both acting, but they're not onto the same object. Equal forces can produce different accelerations if the objects have different masses, making the forces, yeah, they're still the same, but they're doing kind of different things. This law explains everyday actions. This law explains everyday actions like walking, swimming, anything like that, running, all of our everyday actions. There are a lot of relevant formulas, but the main one that most, I know, physics classes use is the F times the AB equals negative FBA, meaning that the forces exerted on object A and B are perfectly equal in magnitude, but opposite in directional sign. So if you were to like draw the square, they'd be the same, but going in different directions. There's also the simultaneous existence. Action and reaction forces happen at the very exact same time. One force does not cause the other to happen after a delay. They're simultaneous products of a singular mutual interaction. There's a requirement of two bodies. A single isolated object cannot experience or exert a force. Every force interaction strictly requires a minimum of two interacting physical bodies. So there has to be at least two things, and Newton makes that very clear in all of his, especially this formula, that all of them have at least two in there. There's not just A and A, it has to have the A and B. Equality of magnitude, no matter how massive one object is compared to another. Say like, I guess a giant truck to a tiny little bug, or the world versus a person, the absolute magnitude of the force exerted on both objects on each is identical for every single collision. We also have in our little photo P equals md. As you can see, there's still two different things either way. Okay. And that's for relevant formulas and constant reference. Okay. Relevant fields. The Newton's third law for every action is opposite equal reaction is used in most engineering things, especially for rocket launches. It explains the rocket launches themselves and helps with the space exploration. For engineering, it's used to design safe and efficient machines, which can also be put into rocket science as well, because they have to make safe rockets. It also applies to sports like swimming and jumping and running. So all of them, you have to have the opposite and equal reaction in order to actually get that everyday movement, which, as you can kind of see in our little boat guy, he's pushing off with his reaction, the boat is moving. It's important in transportation, including cars, boats, and airplanes, as far as how the propellers work, how the oars work, or the airplanes, the wings, the engines, the cars, the engines, everything like that, the tires moving with it, and it just explains everyday motions through action and reaction forces. For 1.4, we have the scientist. The scientist is Isaac Newton. A little bit of him. Newton developed the three laws of motion that explains how objects move. The third law of motion explains that every action force has an equal and opposite reaction, and his work is the foundation of classical mechanics, because it gives you that why and how and what everything's actually doing and how it's working the way it is. It boosted transportation, space exploration, and engineering. It all still relies on Newton's discoveries, and all of it follows his basic laws and principles that he is given, as well as all of the formulas he is given, which we already discussed. Okay. In the original experimentation process, he tested his law using two swinging pendulums. You'll also kind of see them sometimes where it's like the balls all lined up with each other. You like press and it moves. The pendulums are released to collide at the exact same time, and he measured their motions before and after the impact in order to figure out what they were doing and to prove that every action has an opposite and equal reaction. The experiment compared changes in momentum as they swung back and forth, and as a result supported Newton's third law of motion. It is considered his most helpful experiment because it is the original one he used. There's a lot of difficulties and complications that can be considered with this. Air resistance is the main one. Newton was aware that the effects of the external dampening force due to everything caused by air could ensure that the pendulum did not attain its theoretical maximum speed at its lowest point as a result of it being completely dropped. Mathematical correcting for arcs. In order to correct for the issue of air resistance, Newton measured the arc deficit, which meant measuring the amount of height in the pendulum loses during one uncollided cycle of swimming from point R to only reaching V, and then correcting the fractional arcs. So when he did it, he had to completely kind of rearrange it. The problem of imperfect elasticity. Collisions do not occur in reality between perfectly elastic objects, meaning there will always be a loss of kinetic energy due to friction deformation and sounds that could mess up his calculations of moment transfer. So it took him a little bit to figure it all out. He did find a solution for the elasticity. He was able to solve the issue of elasticity by testing out various materials. So like we have down here wool, cork, steel, and glass. I'm sure he used others, but to measure their fixed ratio of rebound velocity over impact velocity coefficient of restitution. As you can see, we have our two little A and B reaction pairs. Okay. And I don't know my part. There it is. Motivation for experiment present. Newton wanted to improve earlier theories about collisions. He tested the ideas with real experiments to gather evidence, and his goal was to prove that forces come in pairs, so there's always the AB or BA. He worked to explain motion with clear mathematical laws, and his research became the foundation of classical mechanics.